Welcome back. In this video, we are going to solve problem 8-18 that is taken from chapter number 8, Combined Loading. And the book name is Mechanics of Material by RC Hibbeler. So statement of the problem is the vertical force P acts on the bottom of the plate having negligible weight. Determine the shortest distance D to the edge of the plate at which it can be applied so that it produces no compressive stress on the plate at section AA. The plate has a thickness of 10 millimeter and P acts along the central line of this thickness. So you can see the figure. This is the plate having total length is 800 millimeter, clear, and this P load is applied from this edge at a distance of D. So you have to find this shortest distance D from this edge so that this P should not produce any compressive stress. The thickness of plate is 10 millimeters. So let's start with the solution. So if you cut this beam at section AA and draw the free body diagram, so it will be like this. Okay. This width of the plate is equal to 200 millimeter, which is equal to 0.2 meter. And when you cut it at this point, so you will be having a normal force that will act at the center of this body, and this force is represented as, let this force is equal to P, clear. And this P, the we can take it as N. We should, because P is given in the downward, so let this force is equal to N, and P which is applied at, this is the P force which is applied at a distance of D from this edge, clear. And when you cut it, you will be having a moment as well. So this moment is given as moment M. Also you can see that this is the half of this plate, clear, which this distance will be equal to 0.1 meter, because this will be the half. Okay, so this distance will be equal to 0.1 minus D. Okay, so we'll apply equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So what we have taken is that, let this distance is x, this distance is y, and z is along out of plane. This is z, this is x, and this is y. So sum of all forces along y direction must be equal to 0. So along y direction there is n force which is upward, and minus p which is downward is equal to 0. So it means that this n will be equal to p. Now we will find the moment. So sum of all moment, and let this point is point C. So sum of all moment about point C is equal to 0, and taking the counterclockwise moment as positive. So about point C, one moment is this one, which is counterclockwise, so it will be positive. So I will write plus M, and the second moment is this force P, and perpendicular distance is this one, and this is producing clockwise movement, so it will be negative. So I will write minus P into 0.1 minus D will be equal to 0. So it means that this moment will be equal to P times 0.1 minus D. So this is the moment that is produced. Now you can see that this is the problem of combined loading, in which there is an axial stress, axial force which will produce axial stress, that is N by A, and due to this movement there will be a bending stress, clear. And this bending stress is sigma M is equal to My divided by I. So this is purely case of combined loading. So I will write combined loading, and we know that in combined loading The formula is normal stress is equal to P by A plus minus M into Y divided by I. Since we are talking about compressive stress, so sigma is equal to P divided by A minus M into Y divided by I. Sigma compressive. Okay, so you can see that due to this loading, there will be a movement like this, clear, and it will cause this plate to bend, and the condition is given that select this distance d in such a way that this compressive stress is equal to 0. So we will put 0 is equal to P by A minus M into Y divided by I. So for that A and I, we have section properties. So section property means we have to find area and moment of inertia. So area is equal to, now this is the plate having width 200 millimeter and thickness is given as 10 millimeter. So this is the thickness 10 millimeter. So this area will be equal to 200 millimeter, which is 0.2, and thickness is 10 millimeter, which is 0.01 meter. So when you multiply it, you will get the area, or area will be 0.2 into 0.1, and the unit will be square meter. Now we'll find I about what x is, or I is equal to 1 over 12 BHQ. Now you can see this is the neutral axis, which is about z. So Iz will be equal to, this is the B and this is the height h. So 1 over 12 B is 0.01, clear, and height is 0.2 Q. Okay, so now we have the unit will be meter power 4. Now you can put it in this formula again. So you will get 0 is equal to P by A. So P is equal to N, or it is P. So P divided by area is 0.2 multiplied by 0.01 minus M is P times 0.1 minus D divided by 1 over 12, 0.01 into 0.2 whole cube. So this will be equal to 0 and this term will be equal to so if you simplify it and take P as common, so you will get P minus 1000 plus 1500. 15,000 into D is equal to 0. What you will do is that you will multiply 0.2 with this, and you then divide 1 with this value. So it will be 500 P. And again, you will multiply P with this and P with this as well and divide by this. So you will get this values. Okay. Now from here you can see this is P and this is another term. So their multiplication is equal to 0. It means either P is equal to 0 or minus 1000 plus 15,000 into D is equal to 0. Since P is not equal to 0 because P load is applied, clear, so therefore minus 1000 plus 15,000 into D is equal to 0. So 15,000 D is equal to 1000 and D will be equal to 0.0667 meter, or in millimeter D will be equal to 66.7 millimeter. And this is the shortest possible distance from this edge. If you select this, D is 66.7 millimeter, and apply the load of P, so it will produce no compressive stress in this plate. And the distribution of this stress in this plate will be like this. Let me draw it as well. So again, you can see that this movement will be like this one and this one. So this portion will be in tension. So here the maximum stress will start from here. So the distribution will be like this. And at other end there is no compressive stress. So distribution will be like this. Okay. So this is the stress distribution in the plate where we have sigma tensile and there is sigma compressive is equal to 0. And that was all about this problem 8-18. I hope you have enjoyed this video and you have learned from it. All the links of different chapter problems are available in description box. So if anyone needs, he or she can go to the description box and click on the given link. And if you have any question regarding my problems, then do let me know in the comment section. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can again ask in comment section. Thank you for watching. Welcome back. Problem 8-19. So this problem is taken from chapter 8, combined loading, and the book is Mechanics of Material by RC Hibbeler. Statement is that determine the maximum and minimum normal stress in the bracket at section AA when the load is applied at x is equal to 0. So you can see this is the bracket, and there is a load of 100 kilonewton that is acting at a distance of 15 millimeter from this edge. So this load is lying on this point, and it is given that x is equal to 0. It means that x start from here till this end. So x is equal to 0. So load will act on this point. So you have to find the maximum and minimum stress in the bracket. So let's start with the solution. So if you cut this section at section AA and draw the free body diagram, so I will draw it like this. It will be like this one. Okay, now you can see that you have a force of 100 kilonewton in at this point. This is 100 kilonewton, and when you cut it at section AA, this is section AA, clear. So you will be having a normal force that will be perpendicular to this surface and through the mid of this section AA, and you will having a moment as well, M. This is load N, clear. Also you can see this distance is given as 200 millimeters. So this distance is 200 millimeter. So half of this will be, if this is the axis, so half will be, this distance will be equal to 100 millimeter, which is in meter is 0.1 meter. Now we'll apply equilibrium condition that sum of all forces along y direction, or you can say let this is your x distance, clear, and this is your y distance, clear. Let this is your y, this is your x-axis, this is your y-axis, and this is your z-axis. So sum of all movement about sum of all forces along z direction must be equal to 0 and force upward taken as positive. So you can see one force along z direction is minus 100 kilonewton and the other one is N, and that is upwards. So it will be equal to, the sum must be equal to 0. So it means that N is also equal to 100 kilonewton. Now we will find moment and let this point is point C. So sum of all moment about point C must be equal to 0, taking the counterclockwise moment as positive. So about this point C, one moment is this reaction moment, that is clockwise, so it will be minus. Another moment will be 100 into perpendicular distance is this 0.1, and it is producing counterclockwise movement, so it will be positive. So I will write minus m plus 100 into 0.1 is equal to 0. So it means that moment is equal to 10 kilonewton into meter. So you can see that this is the moment and this is the normal load. So if we replace this force to this point, so you will be having a moment in this direction as well. So this is the case of combined loading. You can see you have a normal force and which produce axial force which produce normal stress, and this moment m will produce bending stress. So we will write it that it is the combined loading, case of combined loading. So we know that we have stress is equal to P divided by A plus minus M into Y divided by I. Okay. So here you can see this, both these two forces, this and this, they are producing compressive stress. So I will write it, sigma is minus P by A plus minus My over I. Now for tensile loading, for tensile I will write it, sigma is equal to minus P divided by A plus M into Y divided by I. That is for tensile stress. And sigma is equal to minus P divided by A plus minus M into Y divided by I. That is for compressive stress. So we will find both stresses. Okay. So you can see that due to this movement like this portion will be this portion will be in compression and this portion will be in tension. Also, we will find the section properties A and I for the section properties. So this is the area where this load is going to exert. This is the area. Okay, so this area is equal to 30 millimeter multiplied by 200 millimeter. So 30 millimeter is 0.03 and 200 millimeter is 0.2 meter. So you will get the area will be equal to 0.006 square meter. Now we'll find I. So if I draw it like, if I draw the section like this, so you can see this distance is x, height which is equal to 200 millimeter. This is the x direction. This is the y direction which is equal to 30 millimeter, and z is out of plane, so this will be the neutral axis. Okay, so I for the rectangular cross section will be equal to 1 over 12 bh cube. So b is 30 millimeter, which is 0.03, and height is 0.2 whole cube. So when you calculate this, you will get I will be equal to 20 into 10 raised to power minus 6 meter power 4. Now you have I and A, so we will get sigma. Okay, so here you can see that this loading will be like this. The movement will be like about y-axis, so my. So I will write movement about y-axis will be this one. Clear? So you can see this portion will be in compression and this portion will be, sorry, the loading is like this and this. So it means that this portion, which is the left side, will be in compression and this right side will be in tension. So I will first find compressive stress, which is sigma L left is equal to compressive minus P divided by A minus M into Y divided by I. So P, value of P is 100 kilonewton. So 100 into 10 raised to power 3 divided by area, which is 0.006, minus moment, which is 10 kilonewton into meter. So 10 into 10 raised to power 3 divided by I is 20 into 10 raised to power minus 6, and C is distance from neutral axis till top. So this is C. So C is 100 millimeter. So in meter it is equal to 0.1. So I will multiply Y is equal to C, because C is the maximum distance and Y is the distance from neutral axis to anywhere. So if Y is equal to C, so it will be this distance. Clear? So C is 0.1. Okay. So this is stress from the left side, which is compressive, and when you calculate it will be minus 66.67 into 10 raised to power 6 Pascal, or you can see that this compressive stress is minus 66.67 megapascal. Now what we will do is that we will find sigma r, bending stress, or normal stress from the right side, which is equal to P by A minus P by A plus M into Y over I, that is tensile 1. So minus, this is the minus 100 kilonewton. So 100 into 10 raised to power 3 divided by area is 0.006 plus M, which is 10 into 10 raised to power 3 divided by I is 20 into 10 raised to power minus 6. And what is the the Y? This is your neutral axis. Okay. So now from this right side, Y is distance from neutral axis till this point. So neutral axis till this point, and this is also 0.1. So 0.1, that is sigma tensile stress from the left region. So we will get sigma r, when you calculate it you will get it 33.3 into 10 raised to power 6 Pascal. Since it is positive, so we can say this is in tension. And that was all about this problem 8-19, in which this portion was in tension, which is the right side, and this portion, which is the left side, is in compression. And you have seen and you have calculated the minimum and maximum stress. So this is the maximum stress and this is the minimum stress. I hope you have enjoyed this video. Keep watching and supporting me like this. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-20. So this problem is taken from chapter number 8, combined loading, and the book name is Mechanics of Material by RC Hibbeler. So statement is determine the maximum and minimum normal stress in the bracket at section AA when load is applied at X is equal to 300 millimeter. So you can see this is the bracket where a load of 100 kilonewton is applied. The direction of X is given from here, this line. So at here X is equal to 0, and you can increase the X from this line. And you have to find the maximum and minimum normal stress when you section it at AA. So let's start with the solution. So first step is that you can see that this distance is 200 millimeter and this is 150. So it means that total distance is 350. So this is the total distance, which is 350, and it is given that this load is applied at 300 millimeter. So it means that this load is applied at this point. Okay, so what we will do is that I will draw a free body diagram. So this total distance is 350. And this load is applied at a distance of 300 millimeter from this region, from the start. 300 millimeter from this, which is 100 kilonewton. So when you section it at section AA, this is the line of section AA. So definitely you will be having a normal force which will be at the center of this section. Let this force is represented as N, and you will be having a moment as well. So what we will do is we will find this distance is given as 200 millimeter, and this distance remaining is 150. Okay, so we will find the equation of equilibrium. For that I will show you, let this axis is y axis and this axis is x axis and this vertical axis is z axis. So you can see that sum of all forces along this z-axis must be equal to 0 and upward force is taken as positive. So about this z-axis, the force, vertical forces are this 100 kilonewton which is shown over here, and this n force. So their sum must be equal to 0. So minus 100 plus n will be equal to 0. So it means that this normal force will be equal to 100 kilonewton. Now we will find this moment. So sum of all moment will be equal to 0 and about this point C. So let this is the center line of this axis. So this is your point C. Clear? So sum of all moment about point C is equal to 0 and taking the counterclockwise moment as positive. So about this point C, one moment is reaction moment which is counterclockwise, so it will be positive. So I will write M. The other moment will be due to this force 100 Newton and this perpendicular distance, which you can see that this is 100 and this is also 100. That is 200. So this distance is 200. How? This is 100 and this is 100. This is 150, so it is 50 is left over here, so this is 100, so 200. So I will write it distance from this till this point is 200 millimeter, and this is producing this vertical force into perpendicular distance will produce clockwise rotation about point C. So I will write minus 100 into 0.2. 200 millimeter is 0.2 meter. So from here you will get this moment will be equal to 20 kilonewton into meter. Now we know that this is the case of combined loading. You have a normal stress and you have a moment. So due to axial stress, due to axial load, there will be axial stress, and that will be equal to minus P by A. Why minus P by A? Because this is compressive force. Clear? So again, you can also say if you remove this 100 Newton over here, so you will be having a moment as well. So the load is compressive and plus minus M into Y divided by I. Okay, now we'll find this section properties, which is A and I. So section properties, you can see that area which is equal to which is the area of at section AA. So this is the area. Let me choose another color. This is the area over which this force is applied. So this area is equal to 200 millimeter by this 15 plus 15, 30. So 30 millimeter is 0.03 and this width is 200. This distance is 200 millimeter, which in meter is 0.2. So when you solve this, you will get area is 0.006 square meter. Now what about I? So I, moment of inertia. Uh, so this is your y-axis, clear, y-axis, and the moment which is produced, sorry, this is the y-axis, this is not the y-axis, this y-axis is along this direction, clear, and you can see you have a moment which is in this direction. So we will take the moment of inertia about this y-axis. So I will be equal to, this is your breadth which is 30 millimeter, and 0 point sorry, this 200 millimeter will be the height. So I is equal to 1 over 12, b is 0.003, sorry, not 003, 0.03, clear, 0.03, and height is 0.2 whole cube. So when you calculate it, you will get this I will be equal to 20 into 10 raised to power minus 6 meter power 4. Okay, you have A and I, so you can find, you can see that due to this movement, this will bend like this portion will be in compression, and while this portion will be in tension. So this left side will be in tension, clear, and this right side will be equal to in compression. So we will take sigma L, which is the left side and that is in tension, is equal to minus P divided by A plus M into Y divided by I, tension. Okay, put the value is equal to P or N is equal to same, which is 100 kilonewton, so 100 into 10 raised to power 3 divided by area, which is 0.006, plus moment, which is 20 kilonewton, so 20 into 10 raised to power 3 divided by I is 20 into 10 raised to power minus 6. And what about C? C is distance from neutral axis. So this was your neutral axis, and till this distance is your C, which is 100 millimeter, and this 100 millimeter is actually 0.1 meter, so which is sigma L. So when you solve this, you will get it 83.33 into 10 raised to power 6 Pascal, or you can see sigma L stress at the left side will be equal to 83.33 megapascal. Since this value is positive, so it means that left side is in tension. Now we will move towards sigma R, which is in compression, so it will be equal to minus P divided by A minus M into Y divided by I. So put the values, minus 100 into 10 raised to power 3 is the value of P, A is 0.006, minus M is 20 kilonewton, so 20 into 10 raised to power 3 divided by I, which is 20 into 10 raised to power minus 6, and C. Now from this portion till this is C, and this C is again 100 millimeter from the neutral axis, so which is 0.1 meter. So when you solve this, you will get the stress at the right side will be equal to minus 117 into 10 raised to power 6 Pascal, or you can say that minus 117 megapascal. Since this value is negative, so you can see 117 megapascal is the stress value at the right side, and that is in compression. So these are the answer of this question, which is problem 8-20. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 8-24 and 8-25 that is taken from chapter number 8 combined loading, and the book is Mechanics of Material by RC Hibbeler. So statement is the bearing pin supports the load of 700 pound. Determine the stress component in the support member at point A. The support is 0.5 thick. And in 8-25, determine the support stress component in support member at point B. So you can see this is the bearing pin that supports 700 pound force. So you have to determine the stress component at point A and at point B. The thickness downward is shown over here. You can see this is point A, this is point B, and inside this screen you can see the thickness is 0.5 inch. So let's start with the solution. So first step is that you can see if you cut this beam over AB, so you will be having a shear force clear which will be in this direction. Let this is V, and when there will be a normal force along this axis, and this will be equal to N, and there will be a moment as well, M. This moment is equal to M. Now you can see that this line is perpendicular to this surface, and this line is perpendicular to this axis if we draw. So this angle will be also 30 degree. So I will draw it 30 degree perpendicular line from this. It will be this will be 30 degree as well. Similarly, if you take the parallel of this axis at this point, so this will be also 30 degree. So again I will zoom it out, and we will take a parallel line to this. So this will be 30 degree. Now our normal forces are in this direction and shear forces are in this direction. So we will take this as new coordinate x dash, and this will be equal to y dash. So you can see that this member 700 pound will have two component, one along x dash direction and other one is along y dash direction. So this is fy dash and this is fx dash. So we'll first find fx dash. So cos of theta is equal to base, which is fx dash, divided by hypotenuse, that is 700. So this fx dash will be equal to 700 into cos of theta, which is 30 degree, and fy dash will be equal to 700 into sine of 30 degree, because when you take sine of theta, so theta are 30 degree, this is theta, so it will be equal to fy dash over 700. So from here you will get fy dash will be equal to 700. Now we'll apply equation of equilibrium. The first equation of equilibrium will be sum of all forces along x dash direction must be equal to 0, and force in this direction is taken as positive. So you can see one force is this one, which is normal force, and other one is this fx dash. Their sum must be equal to 0. So n minus 700, fx dash is 700 cos of 30 degree is equal to 0. So from here you will get n will be equal to 700 into cos of 30 degree. So n will be equal to, after calculation, it will be 606.218 pounds. So this is the normal force acting along the axis, or axial force. Now you will find sum of all forces along y dash direction must be equal to 0, and force taken in y dash direction is taken as positive. So you can see one force along y dash is this V, which is upward, so it will be minus v, and the second one is downward, which is fy dash. Their sum must be equal to 0. So minus v plus fy dash. So fy dash is 700 into sine of 30 degree. So it means that their sum must be equal to 0 for equilibrium condition. So it means that this v is equal to 700 into sine of 30 degree, and we will get v is equal to, v is the shear force, and that is equal to 350 pounds. Now you have this n and v, so we will find moment. So for moment we will write, let this point is point O. So sum of all moments about point O is equal to 0, and taking the counterclockwise moment as positive. So about this point O, one moment is this one, which is counterclockwise, so it will be positive. So m. The second moment, if I zoom it, so and draw a vertical line from this 700 force. Let me zoom it. If I draw a vertical line from this, so it will be like this. Now you can see that this is the distance. This is the perpendicular distance into this 700 force, which will produce a clockwise rotation or movement in this, about this point O. So how you will find this distance? Let me tell you. As you can see, this distance is 2 inch. So this distance will be equal to, if you take sine of 30, so sine of 30, let this distance is x. So sine of 30 will be equal to x divided by 2. So x will be equal to 2 sine of 30. Since you can see this total distance is 1.25 inch, this is 1.25 inch. So the remaining this distance will be equal to 1.25 minus x. So 1.25 minus 2 into sine of 30 will be this perpendicular distance. This distance. This will be, again, this force into this perpendicular distance will produce counterclockwise rotation in this direction. So I will write it that minus 700 into 1.25 minus 2 into sine of 30 degree will be equal to 0. So when you calculate it, you will get moments comes out to be 175 pounds into inch. Now you have this moment, and this is a case of combined loading. Combined loading. How? Let me tell you this. You can see you have a axial stress, axial force N, and you will have a moment that is also producing bending stress. So one stress and one a normal stress is due to this axial load, and other stress will be due to this bending. So we will write it, sigma will be equal to N by A plus minus M into Y divided by I. In first part, we have to find the stress components at A. So what we will do is that this is point A. You can see you have a movement like this, clear. So you can see that upper one will be in compression, and lower one will be in tension. So sigma A will be equal to, is in compression, so N over A, and this is compressive stress, minus My divided by I. So put the value, N is 606.218 divided by area. You can see that cross section is given as 0.75 multiplied by 0.5. So I will write it 0.75 multiplied by 0.5. minus moment is 175 divided by I is 1 over 12 bh cube. So 1 over 12 b is 0.5 and height is, our thickness is 0.75. So 0.5 multiplied by 0.75 whole cube. And what will be the y? So if we take this as a neutral axis, so y will be equal to distance from neutral axis till point A, which is equal to 0.75 divided by 2, and that is equal to 0.375. So when you solve this, you will get bending normal stress at point A comes out to be minus 212, minus 2.12 KSI. Also, we will find shear stress at point A. So we know that shear stress is equal to V into QA divided by I into T. So if this is the cross section that is shown, this is the 0.5 thickness and this is height, which is 0.75, and this is point A, and this is its neutral axis. So you can see there is no area about point A. So QA, which is equal to y dash bar into A dash, since A dash is equal to 0, so QA will be equal to 0. So if this QA is equal to 0, so we know that then shear stress at point A will be equal to 0. So this is the state of stress or stresses at stress components at point A. Now we will move toward second part, or the second question, that is 8.25. So 8.25. Again, all the things you can see that the point B is in tension. So stress at point B will be equal to N by A plus M into Y divided by I. So put the value 606.218 divided by 0 area, which is 0.75 into 0.5 plus moment is 175, and you can see that this is point B. So B is the distance from neutral axis till B is 0.75 divided by 2, which is equal to 0.375 divided by I, which is 1 over 12, 0.5 into height is 0.75 whole cube. Okay. So when you solve this, you will get bending normal stresses at point B comes out to be 5.35 KSI. Now what about the shear stress at point B? So shear stress at point B is equal to V into QB divided by I into T, and you can see this is a point B. So QB is equal to Y dash bar into A dash. So there is no area above the B or below the B. So Y A dash is equal to 0. It's mean that QB, which is equal to Y dash bar into A dash, will be equal to 0. So this will be also equal to 0, since I will write since QB is equal to 0. So shearing stress at point B is equal to 0. And these are the stress components at point B. So the answer of 8.24 is this one, while answer of 8.25 is this one. And that was all about this problem 8-24 and 25. I hope you have enjoyed this video. I have given all the links of different playlist of this mechanics of material by RC Hibbeler as in chapter wise. So you can go and you can click on your desired chapter link and you can watch all the problem related to that chapter. If you have any question, you can ask me in comment section. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-28. This problem is taken from chapter 8, that is combined loading, from the book Mechanics of Material by RC Hibbeler. Statement of the problem is the cylindrical post having a diameter of 40 millimeter is being pulled from the ground using a sling of negligible thickness. If the rope is subjected to vertical force of 500 Newton, determine the normal stress at point A and B. Show the result on volume element located at each of these points. So you can see this is a cylindrical post, clear, and it is being pulled from the ground by using a slick that is negligible, and a force of P is applied on the rope, and the value of P is 500 Newton. So you have to find the normal stress at point A and B. So let's start with the solution. So if you cut the post at this and draw the free body diagram, so it will be like this. This will be the post. Clear. There is a load of P at this end. This is P. This is the diameter of this post, and this diameter is 40 millimeter. 40 millimeter. Okay. So when you cut it, you will be having a normal force that is acting at the center of this, and let this force will be N. There will be a shear force which is V, and there will be a moment as well which is M. Okay. So you can see that for finding the shear force, sum of all force along horizontal direction must be equal to 0, and force in this direction is taken as positive. So only V is acting horizontally and there is no other force, so it means that horizontal shear force is equal to 0. Now we'll find this vertical force N. So for that, sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So two forces, one is P and other is one N. Their sum must be equal to 0. So P minus N will be equal to 0. So it means that N is equal to P, and P is given as 500 Newton. Okay. Now we will find this moment. Clear. So sum of all moment about, let this is the axis. Clear. This is the vertical axis X. So sum of all moment about X is equal to 0, and taking the counterclockwise moment as positive. So you can see that moment about X is this one reaction moment which is counterclockwise, so it will be plus. So plus M. The second moment is this force, clear, into perpendicular distance is this one, and this one is this distance is radius, which is 40 divided by 2 is 20 millimeter. So 20 millimeter, and this is producing clockwise movement, so minus P into 20 millimeter. So 20 millimeter in meter is 0.02. Their sum must be equal to 0. So from here you will get movement will be equal to 0.02 times P, and that is 0.02 multiplied by 500, and this movement comes out to be 10 Newton into meter. So now you have all these values. So you can see this is a case of combined loading. I will write it, combined loading. How? Let me show you. You can see that there is a axial force N, and if you move this P to this axis, so there will be a moment as well. So this normal force will produce normal stress, or axial force produce normal stress, and this moment will also produce a bending stress. So you will get the stress will be equal to P divided by A, or N divided by A, because N and P are both are same, plus minus M into Y divided by I. Now we will find I and A for this circular or cylindrical post. So area will be equal to area for this circle will be equal to pi r square, So pi multiplied by r is 20 millimeter, which is 0.02 meter in its square. So you will get area will be equal to 1.256 into 10 to the power minus 3 square meter. Now for I for this circular cross section is equal to pi by 4 r power 4. So pi divided by 4 multiplied by r is 0.02 and its power 4, and when you calculate it, it will be equal to 0.1256 into 10 to the power minus 6 meter power 4. Now you have A, you have I, you have P, you have M. So you can see that here this is the load, clear, and this is the load, and there is a movement at this, clear. So on the side of B there will be a compression, it will be like this, clear. There will be a compression on this side and there will be tension on this side. Okay, and you can see if I draw the cross section of that, and its axis horizontal and vertical. So this will be its point A and this will be the point B. Why? Because you can see that the movement will be like this. So this will be the neutral axis, clear, and this movement is about this x-axis, which is shown over here. So B points lie from it at below, and this is, or you can see if you look at over here, so this is point B and this is point B and this is point A, and it will bend like this. Bending moment will be like this. So this is the neutral axis, clear. So sigma at point A will be equal to P by A. If we take plus, so M into Y divided by I. So P is given as 500, area is 1.256 into 10 to the power minus 3, plus movement is 10, and Y, what is the Y? Distance from Y till neutral axis till point A, so Y is equal to 0 divided by I, which is 0.1256 into 10 to the power minus 6. So from here you will get sigma A comes out to be 0.398 megapascal. Now we will find the bending stress or normal stress at point B, which is equal to P by A minus M into Y divided by I. Why we have taken minus? Because I have already told you that due to this movement, this upper portion will be in compression and this will be in tension. So this point B will be in compression. So we are taking minus sign. So P is 500 divided by area, which is 1.256 into 10 to the power minus 3 minus 10 into, now you can see y is this distance, YB. Distance from neutral axis till point B. And this is equal to radius, and that is 0.02. So 0.02 divided by I is 0.1256 into 10 to the power minus 6. which will give you sigma b. And when you solve it, you will get sigma b comes out to be minus 1.19 megapascal. So these are stresses at point A and B. Now we will represent them on differential element. So if we take the element A like this, so sigma A is positive, so it means that this will be the normal stress. Sigma A will be equal to 0.398 megapascal. Now for point B, if you draw the stress element or element of at portion B, so you can see this is minus compressive, so it will be minus B. So sigma B is equal to minus 1.19 megapascal. We will write positive because this sign shows you that this is in compression. So this was for B and this was for A. And that was all about this problem 8-28. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also in description box I have mentioned all the links of the all playlist, so you can visit and you can watch your required chapter videos. Thank you for watching. Welcome back. In this video we are going to solve problem 8-29, that is from chapter 8 combined loading, and the book name is Mechanics of Material by RC Hibbeler. So statement is determine the maximum load P that can be applied to the sling having a negligible thickness so that normal stress in the post does not exceed 30 megapascal. The post has diameter of 50 millimeter. So you can see this is a cylindrical post having diameter of 50 millimeter, and you have to find this P that can be applied to this sling of negligible thickness, and the allowable stress in this post should be equal to 30 megapascal. It should not exceed 30 megapascal. So let's start with the solution. So first step is that if you cut the beam or a cylindrical post over here and draw the free body diagram, so it will be like this. Okay, so at this end we have a load of P. Clear. This diameter is given as 50 millimeter, and if you draw the center of for this cylindrical post, so this distance will be equal to 50 divided by 2, which is equal to 25 millimeter. And when you cut it, you will be having a shear force, horizontal shear force. There will be a normal force that will act on the center line of this cylindrical post, which is N, this is V, and there will be a moment about this axis. Let this axis is X. So we will find this by using sum of all forces along X direction must be equal to 0, and force taken in this direction is positive. So you can see horizontal force is only V. There is no other force, so V is equal to 0. Now we will find this vertical force by using this equation of equilibrium, that sum of all forces along Y direction must be equal to 0 and upward force is taken as positive. So P and N are acting vertically, so P is upward, so P positive and N is downward, that is equal to 0. So from here we will get N is equal to P. Now we will find this moment. So sum of all moment about x-axis is equal to 0 and taking the counterclockwise movement as positive. So about this axis we have one moment is reaction moment which is counterclockwise. So I will write plus M And the second moment is this load into perpendicular distance is 25 millimeter, and this is producing clockwise movement, so it will be negative. So minus P times this 25 millimeter, which in meter, in term of meter, is 0.025, is equal to 0. So it means that PM moment is equal to 0.025 times P. Now you have all these reaction forces and movement, so you can see that this is a case of combined loading. You have a normal force N. If we move this P to this axis, so it will be equal to P is equal to N, and you will have a moment as well. So due to this normal loading, we have P divided by normal stress, and due to this moment we will having a bending stress. So we will write combined loading, and this combined loading is equal to P divided by A plus minus M into Y divided by I. So if you look at this figure and draw the cross section, circular cross section, so this is your horizontal axis and this is your vertical axis. So this point B is this one, this is point A. Clear? So we have given that allowable stress is 30 megapascal, that is maximum. So we will take this is point C. So this is allowable stress which is at point C, and we can see this is equal to P by A plus M into Y divided by I. Now you can put the value. P is not available, so P by A is pi r square. So pi into r is 50 millimeter, which is 0.025. R is diameter is 50, r is equal to 25 millimeter, which is equal to 0.025 meter square plus moment, which is 0.025 times P divided by I, which is pi by 4 r power 4, so 0.025 power 4 into Y. Y is distance from neutral axis till point C. So you can see this is the radius, which is 0.025 meter. So I will multiply it 0.025 meter. And that is equal to allowable stress, which is 30 megapascal. So 30 into 10 raised to power 6. So when you solve this at the end, you will get 30 into 10 raised to power 6 will be equal to P divided by 0.625 into 10 raised to power minus 3 pi plus 0.025 square into P divided by 97.6562 into 10 raised to power minus 9 times pi. So when you solve this, you will get at the end P will be equal to 11.8 kilo Newton, which is the answer of this problem. I hope you will be able to solve this. 1 divided by this will give you P, and this term divide by this will give you some factor into P, and when you add both them, that will be any value, and at the end you will get P. And that was all about this problem 8-29. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-31. So statement of problem is determine the smallest distance d to the edge of plate at which the force P can be applied so that it produces no compressive stress in the plate at section AA. The plate has a thickness of 20 millimeter and P acts along the center line of this thickness. So you can see this is the plate, this is the frontal view, and side view will be this one. This is the thickness is 20 millimeter, clear, and height is 200 millimeter. And this P acts along the center line of this plate, clear. So what we have to find is we have to find this distance d from the base so that this P applied has no compressive stress in the plate. So let's start with the solution. So what we will do is, if you look here, we will section the beam or plate over this distance and draw the free body diagram. So it will be like this. Okay, so P is this distance. If I draw it a little larger, so it will be like this. Okay, so if this is the P that is acting over here, this is P, and this is the distance D which we have to find. Okay, and this is the center of this plate. So when you cut the beam over section AA, so you will be having a normal force along this midline, and this normal force is represented as N, and there will be a bending moment as well. So we will find this N and M by using equation of equilibrium. You can see that this total height is 200 millimeter, which is equal to 0.2 meter. So it means that half of this will be 0.1 meter. So this is 0.1, and this remaining is also 0.1 meter. So this distance will be equal to this distance. This distance will be equal to 0.1 minus this D. Clear? Now we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see two forces. One is this one, which is minus P, and another one is this one, which is plus N. Their sum must be equal to 0. So from here you will get minus P plus N is equal to 0. So N is equal to P. So this normal force is P. Now we'll find moment. So let this point is point C. Clear? So sum of all moment about point C must be equal to 0, and taking the counterclockwise moment as positive. So about point C, one moment is this moment M, which is counterclockwise, so it will be positive. So M, the other moment is due to at point C will be equal to this force into perpendicular distance is this one. And this is producing clockwise rotation, so it will be negative. So I will write minus P into 0.1 minus D is equal to 0. So from here you will get this external moment will be equal to P times 0.1 minus D. Now this is the moment equation. We are going to find out bending stress. You can see that now here we have two stress. One is the normal force and other is the moment. So if you transfer this force to this center line, so P will be like this, and there will be a moment as well. So this case is now combined loading, that is one is normal loading. The stress, normal stress is due to this normal force or axial force, and the second stress that will be generated due to this bending moment. So we can say that normal stress is equal to N divided by A plus minus M into Y divided by I. So we will find section properties, the area and moment of inertia first, and then we will move toward this bending stress or normal stress. So area is equal to, you can see that this height is given as 200 millimeter, but thickness, this height is 200 and thickness is 20 millimeter. This thickness is 20 millimeter and this height is 200 millimeter. Clear? So area is equal to breadth, which is 20 millimeter. So 20 millimeter is 0.20. Clear? And height is 200 millimeter, which is 0.2 meter. So when you multiply it, you will get the area comes out to be 0.004 square meter. Now we'll find I, moment of inertia for this beam. So I is equal to, for rectangular section, which is 1/12 BH cube. So 1/12 B is 0.020, which is 20 millimeter, and in meter it is 0.020, and height is 200 millimeter, which is 0.2 meter. So whole cube. So when you calculate it, you will get I will be equal to 13.33 into 10 raised to power minus 6 meter power 4. So this is moment of inertia. Now what we will do is that you can see that due to this axial loading, there will be normal stress, and due to this movement, there will be the bending stress. And when this bend, it will be like this. So the upper layer will be in compression, this will be in compression, and lower will be in tension. So you can see that if you put the formula over here, N over A and Y upper distance, we will take minus M into Y divided by I, because this bending stress will be compressive one. Clear? So you have this formula. Now it is given that we have to find no compressive stress condition for this D. So it means that this sigma, which is equal to N by A minus M into Y divided by I. So this sigma will be equal to 0, because this defines the compressive stress. Okay. So this is equal to 0. So we will put N. N is equal to P. N divided by A. So N is equal to P, and area is 0.004 minus M. M is bending moment, which is this one. So minus P into 0.1 minus D divided by I, which is 13.33 into 10 raised to power minus 6, and there is a Y. Y is distance from neutral axis till top. So you can see this is 0.1. So I will multiply it 0.1. So you will get 0 is equal to 250 times P, and when you solve this term, so you will get minus 7500 times P into 0.1 minus D. So it means that 7500 P into 0.1 minus D is equal to 250 times P. P will cancel, and 7500 multiplied by 0.1 minus 7500 into D is equal to 250. So 7500 D is equal to 7500 to 0.1 minus 250, and when you calculate it at the last, you will get D will be equal to 0.06667 meter, or in millimeter D will be equal to 66.7 millimeter. So this is the required distance D from this base where P load will be applied, and it will produce no compressive stress condition. And that was all about this problem 8-31. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Each playlist of every chapter is mentioned in description box, so you can go and you can check every chapter. Thank you for watching. Welcome back. Problem 8-32. So this problem is taken from Mechanics of Material by RC Hibbeler, and this is chapter number 8, combined loading. The statement of problem is the horizontal force of P 80 kilonewton acts at the end of the plate. The plate has a thickness of 10 millimeter and P acts along the central line of this thickness such that D is 50 millimeter. Plot the distribution of normal stress acting along section AA. So you can see this is the plate that is fixed support at this end, and there is a P load that applied at a distance of 50 millimeter from this base. Clear? And the length where it is section is 300 millimeter. So you have to find the stress distribution. So let's start with the solution. So first step is that if you cut the beam and draw the free body diagram, so it will be like this one. This is the force P which is acting. This force P is 80 kilonewton, and that is acting at a distance of 50 millimeter. So this distance is in meter, it is 0.050 millimeter. The total length of the height of this beam is equal to 200 millimeter, which is 0.2 meter. So when you cut the beam or section AA, so what you will have a center axial load, which is represented as N, and you will be having a moment M. Clear? So what we will do is that we will find this M and normal force N. Let this point is point C. So by using equation of equilibrium, that sum of all forces along horizontal direction must be equal to 0, and force in this direction is taken as positive. So two forces minus 80 kilonewton plus N will be equal to 0. So minus 80 plus N is equal to 0. So it means that N is equal to 80 kilonewton. Okay, so we have this, and now we will find moment, and this we will use sum of all moment about point C must be equal to 0, and taking the counterclockwise moment as positive. So about this point C, one moment is this reaction moment which is counterclockwise, so it will be positive. So M, the another moment that is due to this force into perpendicular distance will be here now as this distance. So you can see this is totally 0.2, so half will be 0.1 meter. So this distance will be equal to 0.1 minus this distance. This distance will be equal to 0.1 meter minus 0.050, which is equal to 0.050. Okay. So let me write it. Distance from this till this is 0.1 meter. 0.1 meter. And the distance is 50 millimeter. Okay. So this distance will be also equal to 0.050 meter. So P into P is this one, and perpendicular distance is this one. Clear? Because C will lies at that point, and it is producing clockwise movement, so it will be negative. So I will write minus P into 0.050 is equal to 0. Okay, so from here you will get moment is equal to 0.050 multiplied by P, and we know that P is given as 80 kilonewton. So 80. So moment will be equal to 4 kilonewton into meter. Now you have this moment. So you can see that due to this is the case of combined loading where you have an axial load, clear, and you will have a moment as well, clear. So the axial load produce normal stress, and this moment will produce bending stress. So your stress will be equal to N by A, which is normal load, plus minus the stress produced due to bending moment. So my divided by I. Now you can see that due to this movement m, it will bend like this. So the lower portion will be in tension while upper portion will be in compression. So let this upper point is represented as A and lower point is represented as B, because we are going to plot the stress distribution along AA. So what we will do is that stress at point A will be compressive one, so it will be equal to N by A minus M into Y divided by I, while stress at point B will be tension one, tensile stress, so it will be N by A plus My divided by I. So we'll first find sigma A. Sigma A is equal to N is 80 kilonewton, so A 80 into 10 to the power 3 divided by area. So thickness of this plate is given as 10 millimeter. So this is the height. This thickness is 10 millimeter, which is 0.010 meter, and height is 0.20 meter. So area will be equal to 0.010 multiplied by height, which is 0.20. Clear? Minus moment, which is 4 kilonewton. So 4 into 10 raised to power 3 multiplied by y. Y is distance from neutral axis till topmost, that is 0.1 meter. Okay, so we'll put 0.1 divide by I. I is 1 over 12 BH cube. So B is 0.010. Clear? And H is 0.20 whole cube. So when you solve this, you will get bending stress at point A comes out to be minus 20 into 10 to the power 6 Pascal, or you can say that sigma A is 20 megapascal, and that is in compression. Okay. For this portion, we know that stress at point B is equal to N divided by A. N is 80 into 10 raised to the power 3 divided by same area, which is 0.010 into 0.2 plus moment, which is 4 kilonewton, so 4 into 10 raised to the power 3. And now you can see Y is distance from neutral axis till point B, which is again 0.1 meter. 0.1 divided by same I, which is 1 over 12, B, which is 0.010, and 2 H, which is 0.2 cube. So when you solve this, you will get sigma B comes out to be 100 megapascal. 100 into 10 raised to the power 6 Pascal. So which means that sigma B is 100 megapascal. Since this is positive value, so we can see that sigma B is in tension. Now you have both these two values. So let me show you how to draw the stress distribution. So this is the plate. This is the half of the plate. Clear? The total height is 200 millimeter, which is 0.2 meter. Clear? This was point A and this was point B. So at point B, we have compressive stress, which is 20 megapascal. So 20 megapascal, if this is the magnitude of 20 megapascal, 20 megapascal. And at B, which is 100, we have 100 megapascal. So this is 100 megapascal. 100 megapascal. The upper one is in compression and lower one is in tension. So in between these two, there will be a point where this stress will be goes to 0, and then it will increase and will create extension or tension. So this is the stress distribution. Okay. Now you can see that this is the line where the stress is zero. So this is actually its neutral axis. In order to find the distance of neutral axis, uh, what we will do is that is if this is total height 0. 0.2 and let this distance is h, this distance is h, so this remaining distance will be equal to 0.2 minus h. Now you can see we have two similar triangle, one is this one and other one is this one. So what we will take the ratio of, if we take 0.2 minus h divided by the amplitude of stress or maximum stress 20, that will be equal to h divided by 100. Why? Because you can see that these are similar triangles, so the ratio of their sides will be equal. So from here 0.2 minus h divided by h will be equal to 20 over 100. So it means that 100 multiplied by 0.2 minus h will be equal to 20h. So 20 minus 100 h will be equal to 20. So 100 h will be equal to okay, this is 20h. So 100 h plus 20h is equal to 20. It means that 120h will be equal to 20 and h will be equal to 20 divided by 120. So 2 and h will be equal to 1 over 6 meter. So h will be equal to 0.16667 meter. So in term of millimeter, h will be equal to 166.667 millimeter. So it means that below line or below plate, this portion of the plate, so h will be equal to 166.667 millimeter. When you go from this line to this point, so it will be its neutral axis. Neutral axis for this beam is that where the bending stress will be equal to 0. So this was this stress distribution of normal stresses acting along section AA, and that was all about problem 8-32. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. Also, all the links for the playlist is mentioned in every description box of the video, so you can go easily to description box and you can click on the link, so it will take you to the required playlist. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-33. And this problem is taken from Mechanics of Material by RC Hibbeler, and it's chapter number 8, combined loading. The statement of problem is control lever is subjected to horizontal force of 20 Newton on the handle. Determine the state of stress at point A and B. Sketch these results on differential element located at each of these points. The assembly is pin connected at C and attached to a cable D. So you can see from this figure, this is the control lever that is subjected to horizontal force of 20 pounds. That point C is pin connected and there is a cable D that is acting. So due to this force, the cable this element exert force on cable in this direction. As a result, force exerted by the cable on this element will be in this direction. So what we will do is that if you draw the free body diagram, I will draw the free body diagram by using the part as red color. So this is the lever. You can draw it separately. This is 20-pound force. So if you remove this pin connection at point C, so there will be a vertical force which is Cy, and there will be a horizontal force which is represented as Cx, and the cable will exert since this will due to this the cable will be in tension. As a result, this force will exert a force downward on the cable. So this will be the F. Let this force is represented as F, or you can see P because there is a point F as well. So what we will do is we will find this force P by using equation of equilibrium, that sum of all moment about point C must be equal to 0, taking the counterclockwise moment as positive. Why point C is taken? Because if we take point C, a moment, sum of all moment about point C equal to 0, so this force will pass through this point and it is not producing moment, so we will only left with this P and this force. So 20 into perpendicular distance, this is 20, and the perpendicular distance about C is 5, and this is producing clockwise, so it will be negative. So minus 20 into 5. The second moment is produced due to this force P, and perpendicular distance is, you can see, 0.5 plus 1.75, which is 2.50. And this is producing counterclockwise movement, so it will be positive. So I will write plus P into 2.50 will be equal to 0. So 2.50 into P is equal to 100. So you will get P will be equal to 40 pounds. Now you have this P. So what we will do is that again in first portion determine the state of stress at point A and B. So B point is there. So if you cut this lever at this point, the cross section is shown over here. So if we cut at this point, we will choose another color and draw the free body diagram. So this is the lever. Okay. So the horizontal force is 20 pounds. Distance is shown as 2 inch. So from here the distance is 2 inch. And when you cut it, you will be having a shear force V, and you will be having a moment which will be in this direction. So we will find this moment and shear force. So for shear force, sum of all force along x direction must be equal to 0, and force in this direction is taken as positive. So 20 minus V will be equal to 0. So from here shear force is equal to 20 pounds. What about movement? So for movement we will find sum of all movement about, this is your point number 1, about point 1 is equal to 0, and taking the counterclockwise movement as positive. So one movement which is counterclockwise is M, and the second movement about this point 1 is 20 into 4, which is clockwise. So I will write M minus 20 into 4 is equal to 0. So M will be equal to 80. Okay. 20 into 2. Sorry, not 4. This is 2 inch. So 20 into 2, which is equal to 40 pounds into inch. Now you can see you have movement and shear force at this point. So we know that bending stress at point B, if I draw this lever over here in 3-dimensional, so this will be like this. There, this is your point BE, and this is your point B. And this will be, since you can see the bending moment will be like this one, so if this is the neutral axis, so you can see the upper portion above this will bend like this. So point B will be in compression. We know that bending stress B is equal to minus m into y divided by I. Clear? So minus 40 y. What is y? Y distance from neutral axis till point B, and this distance is given as, this is 0.3, so this distance is 0.15. This distance is 3, so this is 0.15. So 0.15 divided by I we will calculate for this cross section 0 by 3 by 0.3 inch. So this is square, so it will be 1 over 12, B 0.3, and height is 0.3 whole cube. And you will get I is 0.675 into 10 raised to power minus 3 inch power 4. So you just put the value 0.65 into 10 raised to power minus 3. So you will get bending stress will be equal to 8.89 minus, and the unit will be KSI. So sigma B will be equal to 8.89 KSI, and this is in compression. Okay. Now we will move toward our second part. Since you can see this was your point E and this was your point B, and this was the neutral axis. So we know that shear force is equal to V into Q, since point is B, so VB QB divided by I into T. And Q, we know that QB is equal to Y dash bar into A dash. Since this point lies on outside boundary, so there is no area above it, so A dash will be equal to 0. It means that QB is equal to 0. So since QB is equal to 0, it means that shear stress will be also, shear stress at B will be 0. So I will write shear stress at point B is equal to 0. Clear? Since QB is equal to 0. Now we'll move towards second part to find out the shear stress and bending stress at point F. So what we will do is that we will cut it over here, somewhere here, and draw the free body diagram. So let me draw it. This is point D, where you have a load of P that is acting, and when you cut it at distance, so you will be having a shear force and you will be having a movement in this direction. And this distance from this till this distance is, you can see that this is 0.75 inch. So we will find the vertical force, sum of all forces along this direction, which is, this is your Y dash, this is your X dash. So Y dash will be equal to 0, taking the force in this direction is positive. So P is 40 kilonewton, which is minus downward minus 40 plus minus 40, and minus V is equal to 0. So from here V is equal to minus 40 pounds. The value is minus, it means that we have taken V as downward, but V is negative, so it means that our the direction of V is upward. Direction of shear force is upward. Okay, now we will find moment as well. So sum of all the moment about, let's say this is the point 2 about point 2 is equal to 0, taking the counterclockwise movement as positive. So one movement is this one, which is clockwise, this is negative, and the second movement is p into perpendicular distance is 0.75, this is counterclockwise, so it will be positive. So minus m plus p, which is 40 into 0.75, is equal to 0. So we will get m will be equal to 30 pounds into inch. Now you have shear force and moment as well as. So what we will do is that you can see at here this section, the cross section is shown, which is 0.25, and the height is 1 inch, 0.5 and 0.5, 1 inch. So what I will draw it. This is the triangle. Let me draw it correctly. So this is 0.25 inch and total height is 1 inch. So neutral axis will be 0.5 inch and this is 0.5 inch. Now point A is at this point. Clear? So this is your point A. Again, we know that bending stress at A is equal to sigma m minus m into y divided by I. Clear? And you can see that bending stress at here is like this. So it means that upper surface will be in tension. Clear? You can also write it upper surface is in tension and the lower one will be in compression, so point A. So you can also, instead of, you can write it as stress at point A is m into c divided by I, and this will be in tension because upper portion is in tension. From here you can see upper portion will be in tension. Okay, so you can just put the values. 30 into c is distance from neutral axis till top, which is 0.5. Clear? And divide by I, which we have calculated, or we will calculate for this one. I will be equal to 1 over 12. B is 0.25 and height is 1 cube. So I will be equal to 0.020833 inch power 4. So put it over here. So you will get 8720 psi, and this will be in tension. Let me show you. I have also written over here this formula minus m into y. So you can see that at this point E, you can see that this was the moment there. So upper portion was in compression, the upper was in, let me check it, wait a minute. The moment you can see here is this one. This was like this, so not like this. Let me check. So movement was like this. So that will cause compression at point B. That's why if you take sigma B is m into c divided by I, but since this point is in, this point B is in compression, this point B is in compression, so you can see this stress will be in compression. Okay, now we'll find shearing stress at point A, and again this will be equal to 0 since QA will be equal to 0. You can check that this is point A, so the area about A is not available, so we know that QA is equal to, y dash bar into A dash. So A dash is equal to 0 because at above the point A there is no area, so QA will be equal to 0. So QA is equal to 0, so tau A will be equal to 0. Now we will define the state of stress at point B and E. So for point B, if you take the element, so only stress is sigma B, which is compression. So minus 8. So it will be like this one. This will be sigma B at point B. And that is sigma was 8.89 KSI. Now for point, another point, that is for point A. For point A, if I draw the state of stress element like this, clear? So you can see this is in tension, so it will be like this. There is no shear force, so it will be sigma A will be equal to 720 psi. So this is the sketch, the result on differential element, and these are the stresses at point A, shear stress and normal stress, and this is the normal stress and shear stress at point B. And that was all about this problem 8-33. I hope you have enjoyed this video and you have learned it. Also remember that I have attached all the links of my playlist in description box, that is arranged chapter wise, so you can also find my videos in the description box as well. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-34. So this problem is taken from Mechanics of Material by RC Hibbeler, and that is chapter number 8, combined loading. Statement of problem is the control lever is subjected to horizontal force of 20 pounds on the handle. Determine the state of stress at point E and F. Sketch the results on differential elements located at each of these points. The assembly is pin connected at C and then attached to cable D. So from this figure you can see this is control lever that is subjected to 20-pound force, and this point C is pin connected, and this mechanism is connected with this cable at D. So we have to find the state of stress at point E, which you can see this is cutted, and this is point E, and at F, that is cross section. On cross section we have been given F point is this one. So let's start with the solution. So first step is that you can see that this wire, this cable will exert a force on the element which will be downward, because you can see this force is in this direction, which is causing the tension in this cable. As a result, cable exert force on this element in downward direction. So what we will do is that we will draw the free body diagram. Member CD and lever as free body diagram. So let me draw it. This will be like this is the lever where there is a 20 pounds force applied. So distance of this lever from this point, this is point C. From this point C is given as 5 inch. This is 5 inch. And at point, this is point D. So at point D you will be having a cable force that will be acting downward. Let this is force P. Clear? So when you remove this pin supported, so you will be having a reaction force in Y direction. Let this is CY, and in X direction this is cx, and the distance between this point D and this point C, this distance is, you can see, 0.75 plus 1.75, which is 2.75. So we will apply equation of equilibrium that sum of all moment about point C must be equal to 0 and taking the counterclockwise moment as positive. Why we take moment about point C? Because these two forces will pass through point C and it's producing no moment, so only this force and this 20 Newton force will subjected to this moment. So I will write first moment is 20 into 5, and this force 20 and perpendicular distance is this 5, and this is producing clockwise movement, so it will be negative. So I will write minus 20 into 5. Another force that is producing movement is P into perpendicular distance about point C is 2.75, and this is producing counterclockwise movement, so it will be positive. So I will write plus P into 2. This is 2.50, not 75. This is 0.75 and 1.7, 2.50. Okay, is equal to 0. So minus 100 plus 2.50 times P is equal to 0. So 2.5 times 0 P will be equal to 100. So it means that P is equal to 40 pounds. P will be 40 pounds. Now you have this P, so we will move toward our main problem. Is that first what we will do is that we will cut the section at this point and draw the free body diagram. So this is the lever and this is its rod. Okay, the lever is subjected to 20-pound force. Clear? So when you cut it at this point, so there will be a shear force V and there will be a movement in this direction, this movement, and this distance is, you can see this distance is 2 inch. So by using equation of equilibrium that sum of all force along horizontal direction must be equal to 0 and force in this direction is taken as positive. So minus V plus 20 is equal to 0. So it means that shear force is equal to 20 pounds. Similarly, the sum of, let this point is 0.1. So the sum of all moment about 0.1 is equal to 0 and taking the counterclockwise movement as positive. So this is counterclockwise movement M minus this 20 into 2, which is producing clockwise movement. So 20 into 2 is equal to 40. Their sum must be equal to 0. So it means that movement is also equal to 40 pounds into inch. Okay. Now you can see that if we remove this force, so that will also produce a moment. Clear? So due to this moment, there will be bending stress in this rod. So again, you can see that cross section is also given as, the cross section is shown over here. This is point E. Clear? And this distance is given as 0.3 inch and this is 0.3 inch. So if we take the neutral axis will be half of it, which is equal to 0.15 inch, and this point E is this point. Clear? So we know that the bending stress at point E will be equal to M into C divided by I. Bending moment M is 40, C is distance from neutral axis till top, which is 0.15, and we will find I. So I for this square cross section is 1 over 12, 0.3 into 0.3 power BH cube. So I will be equal to 0.675 into 10 raised to the power minus 3 inch power 4. So we can put the value 0.675 into 10 raised to the power minus 3. And when you solve this, you will get sigma E is 8.89 KSI. Sigma E is equal to 8.89 KSI. Also, you can see over here that this is the condition when you remove this force, so there will be a moment. So it means that this will bend like this. And point C is located over this. So this portion, this is point E. This portion E is in tension. This will be in compression and this will be in tension. So this stress is tension stress. Also, we will find the shear stress at point E. So shear stress at point E is equal to V into QE divided by I into T. And QE is equal to A dash into Y dash bar. So this is point E. So you can see there is no area above it. So this A dash will be equal to 0. So it means that QE will be equal to 0. Since QE will be equal to 0, so shearing stress theta E will be also equal to 0. I will write since QE is equal to 0. So this is the shearing stress at point E. So what if I draw the state of stress on the element? Clear? It will be like this. Sigma E is in tension. Clear? So sigma E will be in tension. Okay. So it will be like 8.89 KSI, that will be in tension. This is the state of stress at point E. Shear stress is 0. Now what we will do is that we will move toward the second portion, that to find the state of stress at point E. So if we cut it over here and draw the free body diagram, so it will be like this. So this is point D, where you have a force of 40 pound that is acting downward. Clear? So when you cut it, you will be having a shear force in upward direction V, and you will be having a movement like this. The distance between this point till this is 0.75. Let me show you. So you can see that this is the distance from this till this is 0.75. 1.75 is this distance. So we are taking 0.75. So we'll find this moment, sum of all moment about F, sum of all moment about, let this is your Y dash, new X is Y dash, and this is your X dash. So sum of all moment about Y dash must be equal to 0, and force in this direction is taken as positive. So minus 40 plus V is equal to 0. So V is equal to 40 pound. And moment, sum of all moments about, let this is 0.2. So moment about 0.2 is equal to 0, and taking the counterclockwise moment as positive. So 40 into 0.57 is clockwise movement, counterclockwise movement, so it is positive, minus this movement which is clockwise, their sum must be equal to 0. So 40 into 0.75 minus m is equal to 0. So movement is equal to 30 pound into inch. Now you have this movement and this shear force, so we will move toward finding sigma F. So sigma F is equal to M into C divided by I. Clear? So moment is 30. Okay. And we will find I for this. The cross section is shown over here. 0. This is the cross section. If I draw it 0.25 and this height is 1. So let me draw it. This is 0.25 and this is 1 inch. 1 inch. So this is the neutral axis. So this will be 0.5 inch. And again, so 1 over 12, breadth is 0.25 and height is 1 inch, so 1 cube. So you will get I will be equal to 0.020833 inch power 4. So I will write divide by 0.020833. Now you can see that this point F lies on this neutral axis. So this will be the point F. Let me show you. This is the point F and it lies with neutral axis. So C is equal to 0. So multiply by C. So it means that bending stress is equal to 0 at point F. Now what we'll do is that we'll find shear force. So shear force at point F is equal to V into QF divided by I into T. So V is this one, 40 pound. QF is equal to A dash into Y dash bar. So what is A dash? So point C is this one. So A dash will be this A dash. This will be A dash, which is equal to 0.5 multiplied by 0.25. And what is Y dash? So Y dash is distance from neutral axis till mid of this section. So this is Y dash, which is 0.25. Okay, so Y dash is 0.25 inch. This is QF. So now you can put the values. TF is equal to V. V is 40 pound. QF is 0.25 multiplied by 0.25 multiplied by 0.5 divided by I, which is 0.020833. Clear? And thickness of this is 0.25. So when you solve this, you will get the shearing stress at point F comes out to be 240 psi. Now we will draw the state of stress for this point F. So if you take the element like this F, there is no normal or bending stress, so only shear force. So we will draw this shear force like 240 psi. Similarly at this side it will be like this. So state of stress at point E is this one and state of stress at point F is this one. And that was all about this problem 8-34. I hope you have enjoyed this video and you have learned from it. All the links of playlist of different chapters are available in the description box, so you can visit there and you can click on your desired playlist and can watch the videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-36, that is taken from Mechanics of Material by RC Hibbeler and chapter number 8, combined loading. Statement of problem is the drill is jammed in the wall and is subjected to torque and force shown. Determine the state of stress at point A on the cross section of drill bit at section AA. So you can see this is the drill bit. This is the force that is acting at an angle. Magnitude of force is 150 Newton. This drill is jammed in the wall and the torque T is applied 20 Newton into meter. So you have to find the state of stress at point A. So this is the cross section of drill bit. So you have to find the state of rest at A. So let's start with the solution. So first step is that if you cut it along section AA, so definitely you will be having a reaction force in x direction, this is x direction, so it is nx, and you will be having a shear force Vy in downward direction, clear. And as there is a 20 Newton torque is applied, so on in reaction, the torque reaction T will be this, and this will be in opposite to this torque. And the last thing is that you will be having a moment about z-axis, mz. So this is y-axis, this is x-axis, and z-axis is out of the plane. So moment will be along about z-axis. So we'll find this nx, vy, we will find mz and the reaction torque by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see you have two forces, two component of this force. One is this one, and this component is Fy. I will write it over here. So Fy will be equal to 150. This is theta angle. So sine of theta will be equal to 4 over 5. Sine of theta will be 3 over 5. So this will be its vertical component. And the other component will be this one, horizontal component. And this horizontal component will be equal to 150 into cos of theta, and cos of theta will be equal to 4 over 5. Okay, so vertical component is this one, and it is upward, so it will be positive. So 150 into 3 by 5 minus Vy is equal to 0. So from here you will get the vertical shear force Vy will be equal to 90 Newton. So we have this vertical shear force. Now we'll find horizontal shear force by using equilibrium, horizontal normal force nx, so by using this equation of equilibrium. So nx is in positive. In positive, we take positive x in this direction, y in this direction, and z in this direction. You can choose your own one. Okay, so nx minus this horizontal component, which is 150 into 4 over 5. So from here it will be equal to 0. So from here you will get nx will be equal to 120 Newton. Okay, so you have this nx. Now what we will do is that we will find this torque. So you can see that sum of moment about x-axis is equal to 0. So about this x-axis, one torque is this one, which is 20 Newton clockwise, and the second torque is this reaction torque, that is counterclockwise. Their sum must be equal to 0. So counterclockwise is taken as positive, minus clockwise torque is taken as negative. So what we get is that torque, reaction torque will be equal to 20 Newton into meter. And the last thing we will find is the moment about z-axis. So sum of all moment about z-axis must be equal to 0, and taking the counterclockwise moment as positive. So about this z-axis, one moment is this mz, which is clockwise, that will taken as negative. The second moment about this axis is this horizontal force into perpendicular distance is 125, and third one is this force into perpendicular distance is 400 millimeter. Their sum must be equal to 0. So I will write it minus mz, clear, minus 150 into 4 by 5, which is this component. 150 into 4 by 5 is this component, and perpendicular distance is 125 millimeter, which in meter is 0.125. The third moment is due to this Fy force. So plus Fy is 150 into 3 by 5, and perpendicular distance is 400 millimeter, which is 0.400. Their sum must be equal to 0. So when you solve this, you will get moment about z-axis comes out to be 21 Newton into meter. So now you have all these reaction forces and torques and movement. So what we will do is that we will go to find the state of stress. But before going into that, we will also find the section properties. For example, area, moment of inertia. Okay, so we will first find area. So area of this circular twist drill will be equal to pi r square, and r is given as 5 millimeter, which is 0.005 whole square. So this will be equal to 25 multiplied by pi into 10 raised to power minus 6, and unit will be meter square. We will find moment of inertia I. So I for this circular rod or twist drill will be equal to pi by 4 r power 4. So pi and r is 0. Pi by 4 and r is 0.005 power 4. So we will get 0.15625 times pi into 10 raised to power minus 9, and unit will be meter power 4. The last thing we will find is the polar moment of inertia. So polar moment of inertia is J, and that is for circular shape or body, it is pi by 2 c power r power 4. So put the value pi by 2, r is again 0.005 power 4, and you will get J will be equal to 0.3125 times pi multiplied by 10 raised to power minus 9 meter power 4. Now we will use all these section properties. So first we will find the normal stresses. We know that normal stress. So normal stress is represented at sigma. So you can see here that we have one normal stress is Nx divided by the area will give you normal stress. Another normal stress is due to this bending moment, that is Mz, moment about Z. So this normal stress will be the combination of N by X, Nx by area, Nx by area plus minus M into Y divided by I. So from here you can see that Nx, this is compressive stress, that is causing compression in this rod or twist drill. So we will take minus Nx over A and plus minus moment about Z. Moment about Z is this one, 21 Newton into meter. So 21 into Y. Y is distance from neutral axis till point A. So this distance is taken as positive, which is 0.5 millimeter, and that is 0.005. This plus will be converted into minus because this is the formula. Clear? Divide by I which we have calculated is this one, 0.165 0.15625 times pi into 10 raised to power minus 9. Nx which we have calculated is 120. So I will replace minus 120 because this is his compression, and area is given as 25 multiplied by pi into 10 raised to power minus 6. So when you solve this, you will get the normal stress at point A will be equal to minus 215.43 megapascal, or you can say that normal stress at A is 215 megapascal, and that is in compression. Okay. Now we will move toward shear stress. So shear stress R of will be two shear stress. One shear stress is the transverse shear stress. The transverse shear stress due to vertical shear due to Vy. That will be equal to tau of xy due to vertical shear stress at point A will be equal to Vy into QA divided by I Z into thickness T. So you can see at this point A is the outer surface, and that is away from the neutral axis. So Q area at this point, A area will be equal to 0, and we know that QA is equal to Y dash into A. So Q will be equal to 0, and this whole term will be equal to 0. So there is no shear stress, longitudinal or transverse shear stress, so that will be 0. The other shear stress is due to the torsional shear stress. So torsional shear stress due to torque to T, and that is equal to tau of xz due to torque T at point A will be equal to T into R, where that we represent R with C divided by J. So torque is 20, which we calculated was 20 Newton into meter. So 20 multiplied by C is 0.005, which was radius, and J, which we have calculated, is this one, 0.3125, 0.3125 pi into 10 to the power minus 9. So when you calculate it, you will get 101.86 megapascal. So total shear stress will be equal to tau of xy due to vertical shear at point A plus tau of xz due to torque at point A. So this is 0, this is 101.86. So total shearing stress will be equal to 102 megapascal, and that will be only in xz direction. So this is the shear stress. Now we will represent them on elements. So if you take the element like this, and define the axis. So this was your y-axis, this was your z-axis, and this was your x-axis. So normal stress in the direction of S is minus 215. So we will represent this stress is compressive. So this will be like, this stress will be like 215 megapascal. Now of tau of xz. So xz is this one. So you can see that we are going to plot tau of yz. So in tau of xz, in tau of xz, x is the plane and z is the direction. So x plane is actually yz. X plane is the yz. So yz plane is this one. So in the direction of z, this shear stress will be this one. Similarly, it will be this one. This will be this, and shear stress on other face will be this one. So the value of that is 102 megapascal tau xz. And that was all about this problem 3-8-36. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 8-37. So the statement is the drill is jammed in the wall and is subjected to torque and force shown. Determine the state of stress at point B on the cross section of drill bit in back at section AA. So you can see this is the drilling machine and this is the drill bit which is jammed in the wall. The force that is exerted on this drill machine is 150 Newton, that is at certain angle. All the dimensions are ratios are given. So we have to find the state of stress. If you section it at section, the section is shown, so you have to find the state of stress at point B. So let's start with the solution. So first step is that uh, if you cut this at section AA, so definitely you will be having a normal force that will be in an x direction. You will be having a vertical shear which is Vy. You will be having, this is the torque that is applied, that is clockwise. So in reaction you will be have torque about x-axis. And the one important thing is that you will be having a movement about z-axis. Z-axis is actually out of the plane, so this will be moment mz. So we will find this mz, we will find this torque T, we will find this Nx and Vy by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction is equal to 0 and force in this direction is taken as positive. So Nx is exerted, Nx. The other force is, you can see this is the force 150 Newton. It will have two component. One will be along in this direction, Nx, and other one is along this direction. Sorry, not Nx. This will be, let this is F. So this will be Fx and this will be Fy. And this Fx will be equal to F, which is 150 into, let this theta is theta. So cos of theta is 4 over 5. So 4 over 5. And this Fy will be equal to 150 into sine of theta, and sine of theta is 3 over 5, perpendicular over hypotenuse. So 3 over 5. So Nx minus 150 into 4 over 5 will be equal to 0. So from here you will get this Nx will be equal to 120 Newton. We will find this Ny by using, Vy by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So Vy, which is downward, so minus Vy plus this vertical component which is 150 into 3 over 5 will be equal to 0. So Vy will be equal to 90 Newton. Okay. Third step is that we will find this torque T about x-axis. So sum of all moment about x-axis must be equal to 0 and taking the counterclockwise movement as positive. So you can see this is counterclockwise torque and this is clockwise torque about x-axis. So their sum must be equal to 0. So T minus 20 is equal to 0. So from here T will be equal to 20 Newton into meter. And the last thing is that you have to find this moment about z-axis. So sum of all moment about z-axis must be equal to 0 and taking the counterclockwise moment as positive. So this is z-axis. So one moment is this one which is clockwise minus mz. The other moment will be this force into perpendicular distance is 125 millimeter. This will also produce clockwise. And the third moment, which is this force into perpendicular distance, is 400 and this is producing counterclockwise. So their sum will be 0. So minus mz, clear, minus 150 into 4 over 5 multiplied by the perpendicular distance is 125 millimeter, which is 105 meter, plus 150 into 3 over 5 and perpendicular distance is 400 millimeter, which is 0.4 meter. Their sum must be equal to 0. So from here you will get mz will be equal to 21 Newton into meter. Now you have all these reaction values. So we will, and this sort of problem shows you combined loading where you have normal stress, you have movement about z, you have torque as well as these forces. So we will find the section properties and then we will move toward finding these stresses. So sectional properties. In sectional properties, we have to find the area, and you can see this is the cross section. So area is pi r square. Clear? So pi into r is given as 5 millimeter, which is 0.005 square. And when you solve this, you will get 25 into pi into 10 raised to power minus 6 unit will be meter square. Now we'll find the moment of inertia Iz about z-axis. So for this cross section, the moment of inertia for circular body will be pi by 4 r power 4. So pi multiply 4 multiplied by r is 0.005 power 4 will give you 0.15625 pi into 10 is power minus 9, and unit will be meter power 4. The last thing will be polar moment of inertia, and polar moment of inertia for circular rod having radius r is pi by 2 r power 4. So pi by 2 into r is 0.005 power 4 is equal to 0.3125 pi into 10 raised to power minus 9 meter power 4. Now what we will do is that we will move toward finding the normal stresses first. So let me show you what are the normal stresses that is acting on this system. So you can see one stress, normal stress is this Nx, which will cause compression in this rod, and the second normal stress will be due to this bending moment Mz, which we have calculated. So this normal stress will be equal to at point B will be equal to minus N divided by A axial load, stress due to axial load, minus M into Y divided by I into Z. So N is calculated as 120, so minus 120 divided by area is shown over here, 25 pi into 10 raised to power minus 6 minus M moment Mz. This is Mz. 21. What is Y? So Y, you can see here that Y is distance from neutral. This is point B and this is the neutral axis. So Y will be equal to 0. So 0 divided by IZ. So IZ is 0.15625 pi into 10 raised to power minus 9. So this whole term will be 0 because it is multiplied by with 0. So we will get sigma B stress, normal stress at point B comes out to be minus 1.528 megapascal. So this is the normal stress. Now we will move toward shear stress. So we can see that we have shear stress at point B will be due to shear stress, torsional shear stress, and the shear stress due to vertical shear. This is the vertical shear. So we have two. So first we will find transverse shear, which is due to Vy. Clear? And that transverse shear tau of xy vertical at point B will be equal to Vy into QB divided by IZ into T. So what is QB? So QB is equal to Y dash bar into A dash. So from here you can check it that this is the cross section, this is point B. So this is point B. So this is the area A dash. So which is equal to half of semicircle. So pi by 2 r power square. Okay. And what will be Y dash? So Y dash will be this distance from neutral axis. This will be Y dash. And for semicircle, this Y dash bar is equal to 4 over 3 pi into Y, our distance from neutral axis till this. So which is 5 millimeter, 0.005. So when you multiply both this, you will get QB. So 4 over 3 pi multiplied by vertical distance is 0.005 and area is pi by 2 of semicircle, 0.005 whole square. So when you solve this, you will get QB will be equal to 83.33 into 10 raised to the power minus 9 cubic meter. So put the value vertical shear Vy is 90. 90 multiplied by 83.33 into 10 raised to the power minus 9 divided by Iz is this one, 0.156, 0.156 25 pi into 10 raised to the power minus 9. And what about thickness? So thickness, you can see this is the thickness, which is 5 and 5, 10 millimeter. So 10 millimeter is 0.01 meter. So 0.01. So when you calculate it, you will get 1.528 megapascal. That is the shearing stress, transverse shearing stress due to vertical shear at point B. Now another shearing stress is torsional shearing stress, and that is due to torque, which is equal to tau of xy due to torque T at point B will be equal to T into C divided by J. So one question you will ask that in our previous problem A-36 we have taken tau of x, y, clear? One was tau of xz. Yes, this was tau of xy and this was tau of xz. Now here we have taken both tau of xy and tau of xy. The reason is that you can see that this torque is about x-axis, clear, and this vertical shear is along y-axis. So this y-axis is along y-axis means tau of xy. So the reason is that both this point, this is z-axis. So we are interested to find out the shear stress at point z. So z means z-axis mean xy in xy plane. Z is actually xy plane. So that's why we are taking this. So put the value torque is given as 20 Newton into meter. 20 Newton into meter. C is again 0.005 divided by J, which we calculated was 0.3125 pi into 10 raised to the power minus 9. So you will get 101.86 megapascal. This is the shear stress due to torsion or torque at point B. Now total shearing stress will be at point B will be equal to tau of xy torque T at point B minus tau of xy due to vertical shear because it is downward at point B. So 101.8 megapascal minus 1.528 megapascal is equal to 100.3 megapascal, or you can say shearing stress at point B is 100 megapascal. So this is the shearing stress at point B. Now what we will do is that if you want to express on state of stress element at point B, so let this is the element, small element taken. So this is your y-axis. Here this is your taken as x-axis, and this is your z-axis. So normal stress was 1 minus 152. So we will represent them on the state of stress element. So let me show you it. It is compressive, so minus on this face, this will be minus 1.528 megapascal. And tau of xy is equal to tau b, so x represent plane and y represent direction. So x plane means yz, this is z. X plane means yz. So if I draw it like this, so it will be, this is xy plane, so this is xy and yz, so this plane is x plane. So your tau of xy will be this one. I will choose black color, this one upward, so on top face it will be like this one. Similarly, this is also plane, tau of x plane, so tau of x y in the direction of y, this is tau of x y. Clear? And this value is 100 megapascal. So this was all about this problem 8-37. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also, all the links of my playlist are given in the description box, so you can easily find each and every playlist of every chapter. Thank you. Welcome back. In this video, we are going to solve problem 8-22 and 23 that is taken from book Mechanics of Material by RC Hibbeler. It's chapter number 8, combined loading. So statement of this problem is that the clamp is made from member AB and AC which are pin connected at A. So this is member AB and this is member AC that is connected by using a pin at A. If it is exert a compressive force at C and B of 180, so this at point C there is a compressive stress, clear, which is 180 Newton. Determine the maximum compressive stress in the clamp at section AA. So you have to find the maximum compressive stress at section AA. It is also given that screw EF is subjected to only tensile force. So the stress that is generated in this lead screw is tensile stress, clear. So what we have to find is the maximum compressive stress. So let's start with this solution of problem 8-22. So if you take member AC as free AC as free body diagram, and if you draw it, so let me draw it, it will be like this one. I have drawn it roughly. So this is point A. So if you remove this pin support at A, so you will be having a horizontal force, let this is AX, and there will be a vertical force which is AY, passing through this pin. This is AY. Clear? Stress at point C is given as compressive, which is 180 Newton. So this is 180 Newton. Also, it is given that the stress will be tensile in this lead screw. So lead screw will exert a downward force on this member AC. So let this is the F force, which is not known. Clear? We will also write the distance between point, this line is 30 and this is 40. So if this is the line, so this distance will be 30 millimeter, and this distance is till this center of application of this force is 40 millimeter. Now what we will do is that using equation of equilibrium, that first equation of equilibrium is that sum of all forces along y direction must be equal to 0. Upward force is taken as positive. So you can see one force is ay, the other is 180, and third one is minus fy. Their sum must be equal to 0. So ay minus f plus 180 is equal to 0. So from here you can get that f is equal to ay plus 180. That this is your equation number 1. Now we will, this is point f, or you can see this is f point, okay, and this is force. You can also call, we call it p, okay, p, so that you should not confuse with f and this. Now we will take sum of all moment about point f is equal to 0 and taking the counterclockwise moment as positive. So about this point f, one moment is ay, clear? One moment is ay into ay into perpendicular distance is 30, clear? So if we take moment f at f is equal to 0, so there will be horizontal component. So what we will do is that we will take the sum of all moments about point A is equal to 0. And now we will solve. So about point A, one moment is due to this force P into perpendicular distance is 30. This is producing clockwise, so it will be negative. So I will write minus 30P. The second moment is due to this load 180 and perpendicular distance is 70 millimeter, and this is counterclockwise, so it will be positive. So plus 180 multiplied by 70 is equal to 0. So from here 30P will be equal to 180 multiplied by 70, and this P will be equal to 420 Newton. Now you have this value of P, so put P is equal to 420 Newton in equation 1. So what we will get is that 420 is equal to ay plus 180. So we will get ay will be equal to 420 minus 180, which will be equal to 240 Newton ay. So we have now ay as well, we now have p as well. So what we will do is that you can just cut the section over here. If you cut it over here, let me draw it with black color. If you cut it over here, so you will be having this this ay force, or this force will be transmitted over here, and that will be equal to 240 Newton load, clear? And we will have this force at F, at this force will be equal to 180 Newton, and at F we have this F force acting at this is 420 Newton. And if you want to calculate moment, definitely when you cut it at section A, you will have moment, and this moment is equal to 0. You can also check how, because the sum of all moment about this point, if you take the sum of all moment about this point F will be equal to 0. So you can see that 180 multiplied by 40, that is counterclockwise, will be equal to 240 into 30, and this, the net effect will be, the net moment will be equal to 0. So now we will calculate The maximum compressive stress, we know that compressive stress is equal to, at section AA, this will be equal to load per unit area. So load is 240 240 Newton, and area at this section is given as 15 by 15 millimeter. So 15 millimeter is 0.015 meter, and this is 15 millimeter 0.1015 meter. So when you calculate, you will get maximum stress that comes out to be 1.07 into 10 raised to power 6 Pascal, or you can say maximum bending stress is 1.07 megapascal. So this is the answer of our first part, and this stress will be compressive one. Clear? So again, if you want to, in our problem 8-23, the statement is same, but it is given that sketch the stress distribution acting over section AA. So if this is the section AA portion, this is section AA. Clear? So stress is compressive, so the stress distribution will be over this surface will be this one. Clear? And because there is no moment produced, so there will be no bending stress, only a normal stress, that is sigma maximum, and that is compressive, and it is 1.07 megapascal. So this is the stress distribution at section AA. And that was all about this problem 8-22 and 23. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Also share my videos with your friends so that they may also learn and my channel may also grow. Thank you for watching.